Welcome to another AQA A-Level Chemistry video. This is going to be a continuation from the previous video, which was on hydrogen 1 NMR. This is the second part of a two-part video. And yeah, I'm going to go straight into it without any more hassle. So, I just wanted to make one thing clear about TMS. I wasn't able to get the exact question like I said I was going to do in the part 1 of this video. I'll leave a link in the description to the part 1 of this video. But I have been able to get... There is a question about... the disadvantages and advantages of TMS. I don't worry too much about it. I just a question that I saw and I thought maybe it was useful to get. I wasn't able to get that question, but I was able to get a similar question to that, and I'll be at the end of this video. But I just wanted to clear one thing about TMS because I did kind of talk about it and I wasn't very clear about its properties of TMS. Though you don't need to know too much about it, but I think it helps giving you a better understanding of TMS and its advantages and disadvantages. I mean, its general properties, right? So, tetramethylsilane appears as a colorless, mildly acidic, volatile liquid, a serious fire hazard, mildly toxic by ingestion. So it's mildly toxic by ingestion, but that's if you ingest it, of course. But if not ingested, it should be okay. Again, no one's going to be eating it, but just to emphasize that only mildly toxic by ingestion and inhalation. But it emits acrid smoke and fumes. Acrid meaning pungent, so like a deep kind of deep and unpleasant smell, kind of like rotten eggs. So it emits the acrid smoke and fumes when heated to high temperatures. It's less dense than water, hence how it has a higher volatility than water. So hence where it has such a high volatility. Don't want to say it's misquote something that's wrong, but it's less dense than water and insoluble in water. Sorry, but yeah, it's it being less dense. It's also one of the factors that helps it to enable it to be very volatile, which is one of the good properties that we want of it. So less dense than water and insoluble in water, but soluble in most organic solvents. Used as an aviation fuel and an internal standard for NMR analytical instrument, which is the part that we care about. And that's according to PubChem. I'll leave a link in. That's the wrong link actually, but I'll leave a link in the description so I don't get in trouble. And yeah, that's it. Sorry, but that's just a little problem here. There you go. All right, cool. So I'm actually going to go straight into the video. I just wanted to clear that part up, but I'll go straight into the video now. So, making spectra clear. So the choice of solvent before the spectra is recorded makes the process easier. The process of integration after also makes interpretation of the spectra easier. So first I'm going to be talking about the solvent. Now I talked a little bit about CDCl3, and that wasn't to do with that isn't a reference like TMS. TMS is the reference, but CDCl3, DOD or DTO, DTO as it should be called, D2O and the CCl4 are solvents. Because remember, you have to dissolve your sample in order to actually run NMR, and you'll dissolve it with the TMS. The reason why it's very important is because if you use, for example, if you dissolve your compound in, say, ethanol, right? Well, think about the structure of ethanol, right? I'm going to draw not the full structure here, but I'm going to do this here. CH2OH, right? There's that. If we're doing hydrogen 1 NMR and we dissolve the compound in ethanol, ethanol has 2, 3, so that's 6 hydrogens, 6 hydrogen 1 and 6 hydrogen 1s. I say hydrogen 1s. I'll call it protium. That's the isotope of hydrogen that we're measuring, right? And we have 6 H1s in our solvent, and that's massively going to affect our results because we're dissolving our sample, yes, but we also have to include the ethanol in our sample, and we don't want to do that, right? So how are we going to avoid because we also at the same time we also need to dissolve our compound in a solvent. So how are we going to get around being able to dissolve our compound in a solvent. Remember, most of these solvents have hydrogen one in it anyway, so that's quite of a challenge to get around anyway. So how are we going to dissolve our compound in a solvent, but also get hydrogen one detected from the solvent? Because we're not measuring the solvent here, we just want to measure the sample. So how do we do that? Well, what we do is get rid of this here. We just get a solvent that doesn't have hydrogen one in it. We use CdCl3, CCl4, and D2O. Now, if any of you are wondering what is D is deuterium. Deuterium is another isotope of hydrogen. There's the one that the one that we all know, the one that's in the highest abundance, which is protium, which is one proton and one electron. Deuterium is one proton, one neutron, and one electron. Now, as well as it's also not being hydrogen one, so it can't be detected, it's also got an odd nucleon number. So it's also got an even nucleon number, not odd one. It's got an even nucleon number. Now that's beneficial for us because that, as well as it not being hydrogen one and not being detected for hydrogen one NMR, it's also got an even nucleon number, which means it has no overall spin, and therefore it definitely won't be detected by H2 NMR. So by hydrogen one NMR. And yeah, but in chemistry we don't write it as hydrogen like this, because it's technically deuterium. It's another isotope of hydrogen called deuterium. So H2 hydrogen 2, we call it deuterium, and then tritium, which is another isotope of hydrogen. I believe, based on what I understand, it'll be T. Don't quote me on that, but you never really see tritium for A-level chemistry, but deuterium you should know about, and that's all it is. So D2O really is H2O, but it's obviously it's a H2O of a heavier isotope. In fact, this compound here is actually called heavy water, and it is it's water, but the hydrogen atoms are of different isotope. They're deuterium isotopes. So then deuterium obviously has a higher nuclear number, so it's a heavier. When the nucleus of deuterium is heavier than protium. Protium being hydrogen one. So yeah. Also, I just want to make it clear: hydrogen one NMR is also called proton NMR. Proton NMR, hydrogen one NMR, same thing. I mean, obviously, hydrogen one is just one proton as the nucleus. But anyway, so I just wanted to clear it up. So here are three examples of solvents that we use: CdCl3 or CdCl3, which obviously the isotope here we usually understand as CHCl3, but it's not the same thing. So CdCl3, CCl4, and D2O. They're all solvents that we would use for hydrogen one NMR because it doesn't include hydrogen one. So solvent choice in hydrogen one NMR is crucial because many solvents contain hydrogen ones, and if a solvent contains hydrogen ones, they will appear in the spectrum, and this will cause confusion. So this can be solved by using solvents without a hydrogen ones. So for example, CCl4 or deuterated solvents like CdCl3 or D2O. Deuterated solvents. So deuterated solvents are the same as many protonated solvents, but each hydrogen one has been replaced by deuterium D2 atom. Deuterium atoms have an even nuclear number, as I said before, and so will not interfere with the NMR. Integration. So as I kind of talked about in the previous video, but integration, the area ratios of signals in spectra are hard to evaluate at first glance when signal splitting happens. For example, it's hard to compare the area ratio under a quartet and a singlet. So this area here, I mean, doing this is kind of hard to clearly see what areas here underneath here. So to make it easier, many NMR machines integrate the peaks to give them an accurate ratio. And in your exam, you'll actually see on the sides, they'll make it very clear if it's a 2, a 3, and that's just to let you know that it's a 2 to 3 ratio. They put on some. They probably put it on the side here on the y-axis, telling you what the integration peak is. If not, they'll write it directly next to the peak. So say 2 or put here and a 3 here, just to make it more clear. As some, I don't know exactly the way it will be, but it'll be very clear how to tell it's a 2 to 3 peak. And even if they don't tell you that, if they tell you that 1 is a 1 or a 2, or if they don't write it at all, if it's clear to see that 1 is say they didn't write it at all, right? And you, from this example here, if they didn't tell you, you could assume that this is a 1 to 2 mole ratio. Obviously, it's not, it's 2 to 3 here, but you'd say to it, it's gone up by, this appears to be double that. Or this, if this was 3 times the height, if this was like 3 times the height, you could say that that's a 1 to 3 integration ratio. Did I say mole ratio by accident? I mean integration ratio. The point being, right, they'll give you the information, but if they don't give you the information, they don't say 2 to 3, 1 to 2, it'll be very clear. If they're just giving you one example, you can assume that the lowest one represents 1, and assume the ratio, and then make an assumption saying that looks like it's double the height of this peak here. I could say it's 1 to 2, but either way here, they've given you information here and they told you that it's 2 to 3, so use that and say it's 2 to 3. And there's reasons for that. So below some examples to demonstrate interpreting. I think I've already gone through why the ratios are important in my previous video, but I'll go through that again if even if I haven't. But below some examples to demonstrate interpreting hydrogen 1 NMR spectra. For example, so example 1 dichloroethane, right? So 1 dichloroethane. The spectrum above shows 2 peaks representing 2 different proton environments, which makes sense because we have one proton environment here, and then all of these 3 hydrogens here are in the same environment. So technically there's only 2 hydrogen environments here, so we'd expect to have 2 peaks. We would expect to have we expect this hydrogen here to be a duplet, because this hydrogen, or these 3 hydrogens, that's actually, what, I'll draw it out actually. Let me not do that. Let me do this instead. Let me actually rub this out. I said, all right, I'm just going to put it in. Right? Hopefully this makes it a bit more clear here, right? Put a hydrogen here. All of these 3 hydrogens are in the exact same condition. So we consider that to be all in the same environment. And this is another environment here. Now, I expected these hydrogens to represent a doublet, because it's next to, the hydrogen is bonded to a carbon that's next to a carbon that's bonded to only 1 hydrogen. This is not hydrogen, that's not hydrogen. Hydrogen 1, by the way, obviously. When I'm talking about hydrogen here, when I'm talking about examples here, I'm talking about protein, because that's the only thing that we're measuring. So it's only this carbon here, is hydrogen is bonded to a carbon that's adjacent to a carbon that's bonded to only 1 protein hydrogen. And so therefore that'd be a duplet. But look at the integration here. It looks, if I was looking at the integration here, it doesn't say it here, it doesn't say it in the example, but this peak, right? This peak is almost, you can kind of make examples of 1, 2, 3 times this peak here is 3 times the size of this peak. Now that is what the integration ratio is. They might say in your exam, they might not, as I said before, they might not say it like in this example here, but they might write down on the side saying 3 and 1, and that is relevant because obviously you're trying to work out. They don't give you this compound here. Your job is to use the information from the graph to work out the compound that you have, right? And so you're basically trying to draw this compound using this graph. I've just given it to you here. Well, I've given it to you here. This is all from Seneca notes, so just want to make that clear. But it's been given to you here just to help you make an example, and I'll probably go through, as I said before, I'll do exam questions on this to help you show you how to do it when you're doing an exam question, right? Not today, but I'll eventually in the future I'll do exam questions on that. But but bringing it back to the integration ratios, right? This is 3 times the size of this. So I forget, you can't see my hand gestures again, but this is 3 times the size of this, and that represents that there's 3 hydrogens with that are in the same environment compared to this. It was 3 times as many. That's not what it means. Sorry, it means that there's 3 times as many hydrogens in this environment compared to this peak here, right? And it's important that you understand it's an integration ratio. Don't assume that that there's three hydrogens here and one hydrogen here. No, it means there's 3 times as many hydrogens in this environment compared to this environment. The reason why it's specific to say that, because you may get a situation where there's 2 hydrogens in this environment, right? But there's 6 here. See, it would the ratio is technically 3 to 1. I mean, it would technically be 6 to 2, but it might simplify. Some machines might simplify it down to, or some computers might simplify it down to, 3 to 1. But obviously, most time, to make it less confusing to you, it will say 6 to 2. But just in case, 3 to 1. It's about understanding that it's not means there's 3 hydrogens here, 100. It means that there's 3 times as many hydrogens on this peak, and 1 times as many on compared to this peak here, right? And as you can see here, there's 3 hydrogens here and 100 here. So by this example here, that means there's 3 hydrogens here on this peak, which represents these 3 hydrogens, and then 1 hydrogen here on this peak. Now let's go to the splitting, right? Let's go to this peak here. So I already explained the integration ratio, but what I haven't explained is the splitting on this peak here. Now this makes sense that this would be a quartet, and I can see it's quartet because there's 1, 2, 3, 4, and it's because, remember, we're following the n+1 rule here, right? There's 3 hydrogen. This peak represents this hydrogen here. It represents this hydrogen here, and this hydrogen is adjacent to a carbon that has bonded to 3 other hydrogens. So this is why proton NMR is so much better, because we're able to get much more information. Even though it may be a bit more difficult to understand, over time you will get. I know you're probably looking at this and saying this is really confusing, but I'm trying my hardest to make it as simple as possible for you guys to understand. But what you need to get is that it's a benefit that it's giving you more information, because it's telling you as much information that you need to answer the question. That's why I think hydrogen H1 NMR is very useful. So here, so as I said before, so this hydrogen is bonded to a carbon that's adjacent to a carbon that's bonded to 3 hydrogens. And so if you follow the n+1 rule, right, that'd be 3 + 1, and that's 4 hydrogens in total. And that's why, so that's 4 peaks in total in the splitting, or 4 splits in the peak. 1, 2, 3, 4. And now if you're looking at this, if you're doing the other way around, right, because that's what we're trying to do here. Realistically, I'm just explaining it to you, knowing what the compound is already. But if we're doing it the other way around, we have to take into consideration that so you have to just basically, if you're doing the other way around, you're saying that there's 4 splits here. There's 1, 2, 3, 4 splits, and I have to take away 1, if that makes any sense. So if I say I can't see this compound at all, which is the truth. That's what you won't be able to see that in the exam. You have to say, I can see a quartet here. I can see a quartet here. So there must be 3 hydrogen. It must be next to a hydrogen, next to a carbon that's bonded to 3 hydrogens. That makes sense. So I'll do n. Technically, I'll be doing n-1 when it comes to the peaks. If that makes any sense. Hopefully, it made sense. Right. Good. And also take into consideration where the peaks are notice how this peak is much, much, much further away than this peak. And I said before, I explained to you why that is. And and what is tell me, even if I didn't look at the data table that they do give me, as I said before, they give you a data table. Have I got it all the way up here? Yes, they give you a data table here. I'm not gonna look for it specifically, because I already know what the compound is. I know it's within. It's going to be roughly here, because we have CLs. So I don't need to worry about that too much. But what I was talking about before was, look how far they are in distance, right? That would tell me that is next to a polar this pK is next to a polar molecule, or next to two polar molecules, because it's so far away from the usual value, which is around 3, I think. So it's next to two polar molecules. I mean, polar molecules are so electronegative that they de-shield that hydrogen. They're pulling electron density away from the carbon and the hydrogen here. Mostly we're talking about the hydrogen here generally, but that means that the bonds are closer towards the electrons in the bond are closer towards the chlorine, and therefore there's less shielding on the hydrogen. And I've already gone through and explained everything to do that in my previous video. I'm not going to go into much deep explanation regarding that. But that's one thing I would help me out understand. So I know that this peak is representing the hydrogen that's bonded to the carbon that's closest to the polar molecules, or bonded to the polar molecules. But yeah, I'm not going to go through every I've got a couple more examples here. I'm not going to go through every single one of them in that same level of depth, but just show you one example here. And it shouldn't take you long. Realistically, with a compound that's this simple, there's only two peaks here, right? There's only two peaks here, so you generally be able to answer this question within 1-2 minutes, maybe less if you do a lot of practice. But for the purpose of explanation, I've just gone a bit faster there. But here, bromodimethyl ether, right? So the spectrum above shows two peaks representing two different environments, different proton environments. Both peaks are singlets because neither of them are adjacent to a carbon with any protons in it. So this is quite common in terms of like it might confuse you if you don't really know what's going on. But let's draw. I'm gonna draw it out quickly because it is a very simple thing, but people may not understand it. So it's an ether. Okay, so notice here there's none of these peaks here. So there's only two hydrogen environments here. These hydrogens are in the exact same environments as one another, as we would agree. They're both bonded to a carbon that's next to an oxygen and a bromine. So both of these hydrogens are in the exact same environment as one another. So that's one environment. That'll be one peak. And another peak here, all these hydrogens are bonded to the same carbon that's bonded to an oxygen. So they're also in the exact same environment here. Now, when regarding how to draw out this compound, right? I look first of all at the integration peaks here. Now, none of these examples have the integration ratios, but this is quite a harder one to tell the difference, right? But realistically, the integration ratio here is 3:2. And this carbon here has 3 hydrogens, so this would be it have an integration of 3, and this will have and this carbon here. So this carbon, you're talking about the hydrogens. We're talking about hydrogen environments. Not the. Let me correct that. That's my mistake. I don't want to confuse people like that. This hydrogen, or these 3 hydrogens will be represented by this peak here. These 3 hydrogens were represented by this peak here, because it's higher, and that's the 3, and this is a 2. Now, in case you get a difficult peak like this, but it doesn't make it clear to see what the integration ratios are, most of these questions, as I said before, when I did the understanding NMR video, I'll leave a link in the description to that video as well. You're not just going to get simple. You're not just going to get NMR. They'll give you information on infrared. They may even give you some chemical tests. So you already kind of have an understanding of what this chemical is by and how many hydrogens it may have. They may even give you a mass spec to tell you how much, or what's the MR of your compound, which may help you out. But so yeah, but if that's so I just want to make it clear, they're not just going to give you only NMR. They give you a lot of other information. Sometimes it will just be NMR, but just want to let you know it's not always just going to be just NMR. They give you a multitude of different types of spectra to get to look at, or not just spectra, just information to help give you your answer. But I say this is an integration ratio. This is 3 because 3 hydrogens within the same environment, and this is 2, and this would be 2 hydrogens within the same environment, right? Now the reason why Sorry, I want to collect my thoughts here. I look at the x-axis here. Obviously, the first thing we'll look at is we'll look at our data sheet here, but I'm not looking at data sheet because I think the data sheet is pretty self-explanatory to see where the points are, and it's like what range the points are within. So, for example, this one, what was the example here? This is what you should do. I'm going to explain why I'm not doing that for this specific example here because I'm just trying to explain to you. But here, this is what 3.4 ish, right? 3.4 ish. So that's roughly, and we know we have a BR in it. So would that make sense? Yeah, that would be 3.4 was within this range. So that makes sense. And the other peak is within what, 5.4, roughly 5.4. 5.4. Let me double check that one again. Let me double check that last peak again. That doesn't mean, 5.4. Okay, let me double check that one again. Because realistically, that follows this here. I mean, it's next to, the reason why this, but actually, that makes a bit of sense now. It's bonded to this, yes, but it's also bonded to a carbon that's not too far away from a bromine as well. So that's probably why this isn't all the different types of hydrogen. There's much more. This is only a shortened version of it. So you probably aren't going to get an example like the one I've shown. They would definitely give you a peak that's within the range that's given for this data sheet. Of course, there's much more hydrogen 1 NMR examples, but this is the ones that they give you. That's the only ones that you need to know. And if it's not there, it's probably because it's not the one that you need to look at, really. So if it's not, if that's that, all the peaks in your exam will be within these ranges pretty much. But as I said, but I didn't want to really talk about that because that's pretty self-explanatory to do. I want you to understand why they're there. Now it makes sense that this peak would be here because it's less shielded, right? This is less shielded because getting it's less shielded from the fact that electrons are being pulled. Electrons are being pulled away from the hydrogen. In terms of this bond here, the electrons within this bond are going to be closer towards the oxygen here because oxygen is very electronegative and has a strong pulling effect. And bromine is also very electronegative and has a strong pulling effect. So it's going to pull these electrons away from this hydrogen. So this hydrogen is experiencing less shielding. And I've already gone and explained why what effect that will have. If you don't remember, then go back to my previous video. Leave a link in the description to that as well. And that's it. I mean, that's pretty self-explanatory there. So yeah, I'm gonna go to the next, and I think this should be the final example before. Yes, it is the final example. So ethanol, right? The spectrum above shows two peaks representing two different proton environments. The peak on the left represents the hydrogen one on the CH2OH because it's deshielded, and the splittings are a triplet and a quartet as expected. Great. So I'm going to just draw out this structure formula. Do I have to really draw this displayed formula? I'm going to draw out the structure formula. I just like doing it like that because it just shows you where the hydrogens are. Now, from what I see here, now, but even before I'm able to, so even before actually looking at the graph, and I just looked straight at the compound, I see one, two, and three different type of hydrogen environments. So that's the first thing I'm looking at here. And you can kind of look at what you have. So you can see there's three hydrogens here that's next to carbon that has two hydrogens here. So at some point I'm expecting to see, we know there's going to be three peaks. I would expect to see a quartet for this, and I'll expect a duplet, so triplet for this, quartet for this, triplet for this, because this carbon is bonded, this carbon has three hydrogens, or this hydrogen really is bonded to a carbon that's adjacent to a carbon with two hydrogens on it, so n plus 1 would be 3. So that would be, this would be a triplet. So these hydrogens here would be represented by a triplet, and these hydrogens here that's on the CH2 is adjacent to a carbon that is bonded to three hydrogens on it, right? So this would be a quartet. Now it's not, but this oxygen here, it's not bonded to a carbon really. So and this hydrogen here, this environment here, it's bonded to the it's bonded to the oxygen on the hydroxyl group. So it's so far away from the carbon here, so this would be detected as having a single peak. It's got no hydrogens next to it really. No hydrogen, so no, it's not adjacent to a carbon that's bonded to a hydrogen really. Because in itself it's bonded to an oxygen. It's not sorry, I should really rephrase that. It's not bonded to a carbon, so it wouldn't be able to detect the carbon next to it, and that's to do with that's the reason for that are a bit more complex, but more to do with shielding. We don't need to know more about that. But when you see a hydroxyl group like this, think singlet. That's what I think singlet. So, and that's what we can see here. We can see a singlet. Sorry, I have to just do one thing quickly. Sorry about that. Sorry, I'm streaming on the same side as well. But say you can see a singlet here. We can see a quartet here, and we can see a triplet, just like we would expect it. Again, these are very simple compounds. The ones that you actually do in your exam are a lot more complex compounds. But as I said, I'll do an exam question to help you understand that, right? I'm actually going to remove these highlighting here because it makes it a bit more confusing to see. But now we need to go through. We know the hydroxyl group here is, so okay, sorry, I forget, I'm doing this the wrong way around because you're seeing, I forget that you're trying to make the compounds. You're not trying to make the spectra. You're trying to make the compound. Sorry. If they just say I mean, I'm only doing this because they've told you what the compound is, but I completely forget that you're not going to be able to see what this compound is. You're trying to work out what the compound is from the spectrum. I forgot about that. My apologies, but okay, that's fine. We're trying to work out what it is, but they're going to tell us, they're going to give us enough information to tell us that it's an alcohol of some sorts, right? And that's from the spectra we can see here. So from the spectra, that should be enough information. We know that it's a singlet peak. But first of all, I look here and say, so I'm really sorry that you guys had to explain that because I made you look like, I made to try and understand that. Sorry, I made you guys think that you could see the structure first and then you look at the spectra, and completely forgot that you're not going to be able to see the structure. You're trying to work out what the structure is. That's kind of throwing me off, but it's not a problem for me. I can work out. I can keep going from here, so that's fine. So right, so we have a singlet here. Do I have to go back to this? Okay, I mean, what's it in? It's in what? It's in 2.6, right? 2.6. A singlet peak at 2.6, right? That can be within the range for a hydroxyl group. That's fine. All right, cool. Now I'm not gonna go to every single point because that's how you should do it. You should you should have the data sheet next to you and be able to see that's a hydroxyl group. That's a carbon. You know, actually, it's only two carbons. There's only two more groups left, so I will do it, right? This peak here is what 1 point say 25 maybe, or 1.25, something around that. No, it's 1.2 really, right? I'm expecting this to be the CH3 because it's so low down it's got such a low chemical shift compared to this group here. So this is what I mean. This is what I'm thinking. Even if you don't know, you haven't got the data sheet right next to you, and such a simple example here, I can tell this must be the CH3, and this is the CH2, because of where they are on this. So the chemical shift here is much higher. I'm expecting that to be the CH2. So this CH3, this is going to be our CH3, right? What, to 1.2. So I assume that's going to be a carbon that's next to a hydroxyl group. Or carbon that's, wait. Yeah. A carbon, yeah, carbon that's next to a hydroxyl group. Yeah, and that can be that there. ROH. That's the hydrogen there, but it's going to be a hydrogen, sorry, not the carbon next to hydrogen, a hydrogen that's next to a hydroxyl group. At 1.2, that's fine, yeah. At 1.2, that's ROH. So, yeah, that's the 1.2 would make sense there. Yeah. And then assume that the last one, which is what, 3.6. 3.6 is the last one. Great. Is this example right? 3.6. Sorry, I forget. Actually, no. The 3.6 is the I forget. This 3.6 would be, what is it? This 3.6 would be this carbon here. I forget. And this 1.2, yes, that makes sense now. The 1.2 represents the CH3 here, so yes, that's fine. All right, cool. So CH3 here, which is 1.2, sorry, I haven't done the NMR in quite a bit of time here, which makes sense. 1.2 for the CH3 here, or the hydrogen that's on the CH3. Makes sense. And then the 3.6 would be next to a hydroxyl group. So, and that's within the range here. An R that's next to a OH. Yep, and yeah, that's just enough from there. Sorry, I haven't done NMR in quite a bit of time, so forgive me if I'm a bit slow. But in my the general point is you have them next to one another, but you can clearly tell here there's only two. There's a triplet here, so there's a triplet here and a quartet here. You can clearly tell there's going to be what you should be doing here. What you should be doing, right, is doing CH2, right? If I have a triplet, it means I have to do n minus 1 really. We'll take away 1 if we're going to find. If that's a triplet, that's n minus 1, so 3 minus 1, 2, 4 minus 1, 3. There's going to be that there, right? And there's going to be a singlet peak. So it means, and this is hydrogen 1 NMR, so we're not going to have carbon. So I can work out, say, right, that's the only possible combination to get the results that I want, right? So I'll write here. That's the only possible combination, because if I do this, if I try to do anything else, well, ethanol is the only it doesn't matter if you put the hydroxyl group here or here, it's still just going to be ethanol. But you just gotta have, it's kind of a little bit of trial and error, but it's also not trial and error. That's a weird thing of me saying, because you have information there to tell you where it is, but at the same time, if you're not careful, it can be a game of trying to say, is it here? Is it here? You kind of have to just look at it from this perspective of, does it make sense? And so if you do that for the longer questions, you're gonna have to say, does this make sense? Does this group here, being here, make sense? Yes, it does, because it says that I've got a triplet, which means that the carbon next to it is pointed to it's the hydrogen. Sorry, the hydrogen. This hydrogen environment here is next to an environment of carbons where there's two hydrogens on it, because it's going to be 3 minus 1, of course, to get 2. So the carbon next to this hydrogen is bonding to a carbon that's adjacent to a carbon that's bonding to only 2 hydrogens in it, and vice versa here, or vice versa I should say, here we've got 4 here, so it means this hydrogen environment It's bonded to a carbon that's adjacent to a carbon that has 3 hydrogens on it. What does that mean? It means, and it's only, these are the only 2 peaks, or only 2 big peaks here, right? That means I've got a CH3 and a CH2, and then another, probably an OH from what we see in OH. And therefore we have ethanol. See, I know I've tried to make, I may have confused you here. Hopefully I didn't, but it's just about seeing the pattern. It's just about seeing the pattern, saying, I've got CH3, I've got CH2, and I know I have an OH. They haven't made it clear enough that it's an OH, but it should make it clear enough that that's an OH from either from the question or from just seeing from the data sheet. What possible combinations could they have? Now, there's only one possible combination. I have CH3, CH2, OH. The idea of NMR is you have your spectra and you're trying to make your compound. You're trying to guess what compound, make an educated guess what your compound is based off the NMR sheet. Hopefully this didn't confuse you. I feel like I probably have confused you. If I did, leave a comment in the description. I'll try and redo this video if you want, so it's less confusing. But yeah, that's what it is. Now I'm gonna go through one. Now remember the splitting and triplet. Can't keep doing this again. The splittings are a triplet and a quartet are as expected here. So as I said before, you kind of just look at the triplets. You look at your splitting. You look at your peaks, and you say, I must have a CH3 here. I must have a CH2 here, because of this. So just try and write down, especially if it's a longer compound, try and draw all the groups out separately. Draw a CH3 out here, a CH2 out here. I have another CH2, but it's in a different environment. What could that mean? And try and put them together. Okay, that goes with this. This goes with that. That goes with that. That's what I mean by why it's a guess, but it's also not a guess at the same time, because they've given you the chemical shift value, so you know roughly what that means with the type of bond they have. So where it could be bonded next to. So yeah, NMR isn't an easy topic at the start, but over time it can be easy. Hopefully this video didn't make it too difficult for you to understand. Now I'm going to do a quick question here. So pause video now and try and answer this question. So this question is about NMR spectroscopy. A compound is usually mixed with tetramethylsilane and either CCl4 or CdCl3. Before recording the compound's hydrogen 1 NMR spectrum, state why tetramethylsilane, tetramethylsilane, tetrachloromethane, and CdCl3 are used in hydrogen 1 NMR spectroscopy, and explain how their properties make them suitable for use in hydrogen 1 NMR. Right. Okay, no problem. Obviously, don't drink tea when you're doing exam papers. Don't follow me. I never did them. Trying to create an exam environment every single time you do papers. I've done my exams, so don't at me. But I'll go straight for it. Now, I've done the boxes here because this is a 2-part question, right? So you want me to state why they're used. So I do one for each. I do a box for each compound to make sure that I don't forget to talk about it. And then I want to explain the properties and how they make them suitable for hydrogen NMR spectroscopy. So, kind of you need to give me a bit of space here. Should I get a timer out? How many questions? How many marks is this? It's a 6-mark question. So I probably didn't get to see that. It's a 6-mark question. Yeah. So if you wasn't able to get that right, it is a 6-mark question. So expect to have, it'll probably either be one who has to have 6 points, or it could be a question where you need to have where you have like one of those like set of, what's it called again, band 1, band 2, band 3. You know those type of questions in the mark scheme where they have to go to cover each certain point. You get band 1 for mentioning 1 point, mentioning 2 points, or covering one side. Band 2, give us decently coherent answer, and then band 3 is covering pretty much nearly all of the content there. So I'm going to set a timer of 6 minutes and try and answer this question. Really, I should have started the timer before answering the question, but I've just remembered now. Right. So I'm going to speak as I'm going through this, right? So I say for all three compounds are inerts, so have a low probability to affect the sample. Say affect the sample, to react with the sample, sorry. To react with the sample. If it's inert, it means inert just means it doesn't react. So now I've kind of talked a bit about all three of them, but I want to make a very specific, right? So, CCl4 and CDSCl3 are solvents. So CCl3. So it's not CCl3, CCl4 really. Sorry, my bad. CCl4 and CDCl3 are solvents. So I kind of covered that. 1, 2. I can take those off. TMS. You can write by bullet point. I'd advise doing it bullet points because you kind of you're saying to examiner where our points are, and it makes it much easier for the examiner to follow. So TMS is used as our standard to provide the reference peak. So I've done those three now. Now explain how their properties make them suitable for use in hydrogen 1 NMR. Now you probably haven't given me. I have to be careful now because I haven't got much space, right? So neither solvent has hydrogen 1, so they use the isotope deuterium, which has no overall spin. Now I'm gonna kind of shorten that one. I mean, how can I say this? So I can say neither solvent has hydrogen 1, so they use the isotope deuterium, which has no overall spin, which won't be detected. So neither solvent has hydrogen 1. They use the isotope deuterium, which has no overall spin, hence won't be detected. I can kind of go and say one thing that we do know about CDSCl3. I forgot to mention it because I only mentioned that because I've done this question. I've done this question before. I remember doing it last year. But CDCl3, I mean for a mock, not for the actual exam. I know that CDCl3 is a polar molecule, and you can just see it here. I mean, if you remember when I did the video about polarity, I should have done that video. This doesn't have polarity because CCl4 doesn't have polarity because sorry, I paused the video. I'll pause that as I'm talking about this now. I'll pause the time as I'm doing this now. But CCl4 doesn't have polarity because even though chlorine is very polar, they're equally distributed amongst the carbon atom. So if you have polar atoms surrounding the carbon equally, the polarity would cancel out because that cancels out by that, and that cancels out by that, and that cancels out by that. Whereas CDCl3 would be polar because it's the polarity isn't cancelled out. DCl, CL, CL, Now, these cancel out, yeah, but overall, is the polarities cancel out because this deuterium here is not the same as chlorine here. Deuterium, remember, the isotopes are different. Isotopes are different forms of the same atom. It's just that it has a different. It's the same atom. It just has same proton number but different number of neutrons. So that doesn't affect the chemical properties. Chemical properties are affected by the electronic configuration. So we know that normal hydrogen is nonpolar. So deuterium is also nonpolar. The it's a polarity difference. It hasn't changed, right? That's the chemical properties of isotopes don't change. Just that they have a different number of neutrons. So we know that hydrogen isn't polar. So you can just say this is polar, but this isn't. Overall polarity is overall this compound is a polar compound. I just want to talk about that one clear there. But there's a reason why that's useful. I'll continue my timer now. If you answer this question, don't stop your timer. Don't stop because of that. I just did it because I wanted to explain that quickly. But CDCl3 is a polar molecule. With covalent character. And a good solvent for organic compounds. So a good solvent for polar organic compounds. CCl4 isn't polar. So CCl4 isn't polar, and is a good solvent for non-polar organic compounds. Sorry, pause this video right here. I need to get a bit more space. Right, and then the last part here, I only have I have 40 seconds left, so I have to be a bit quick. In the exam you get additional paper, so don't worry about if you ran out of time. But the last one here is I talked about. I've explained these two now. Sorry. I've explained CCl4 and CDCl3. Now I haven't done TMS yet, so alright, continue my timer. So all hydrogen 1, I've got 29 seconds left. All hydrogens in TMS are in the same environment. So if my handwriting is kind of butchered, so I just wanted to make sure that you can all see that. So it's not, and also this another point you could say is that it's not difficult to isolate due to its low boiling point. Not difficult to isolate due to high volatility and low boiling point, which is kind of basically the same thing really. But that is it. All right, so here's the mark scheme here. So I haven't got the thing side by side. Yeah, I could probably get it side by side actually. What I'm talking about, I can get it side by side. There you go. So is it here? Or it's the bottom? So I say all three compounds are inert. So in order to get band 3, you need to have all stages covered, and each stage is generally correct and virtually complete. Progression from and then answers communicates coherently and shows a logical progression from stage 1 to stage 2 and stage 3. Right. So oh, actually, one second. So CdCl3 and CCl4 are solvents. So I'm gonna change this to a green pen. Solvents, yes. TMS as a reference, yes. Or standard. Yep, that's fine. I actually covered all three of them there, so that's fine. All of 1A, B, and C. 1A, 1B, 1C. Both have no hydrogen tied to either CDC. Yeah, no hydrogen or no. Neither solvents have hydrogen 1. So atoms will give no signals in spectrum. So won't be detected. Fine, yep. I can say 2A. It's fine. 2B, CCl4 is non-polar. Isn't polar. Yes. Good solvent. So it's in brackets, so I don't have to mention it, but good solvent for non-organic molecules, and vice versa for CDCl3, where it is polar covalent, polar with has, I said, it has covalent character. Yes, polar covalent molecule, good solvent for polar organic compounds. Yes. So 2A, 2B, and 2C. Again, you don't need to have all of, if you covered 1A, 1B, 2A, 2B, and then say you did 3A, 3A, 3B, but not 3C, you'd get 5 out of 6 marks because you covered pretty much everything. It's just that you didn't maybe cover every single part of the question. If you did 1A, 1B, 1C, 2A, 2B, and then 3A, 3B, that would be 6 marks. You just need to, if you need to fully complete one section to get 6 marks at least, and then you can get 2 out of 3 for the rest of them. Now 3A, equipment, 1 signal, TMS, I said all in the same, in hydrogen 1, TMS are all in the same all hydrogen ones in TMS are in the same environment, so I can give that one as well. 3A. And then 3B, I didn't say 3B, but I did say 3C, where it's easy to remove, volatile. Yeah, not difficult to isolate due to the high volatility and low boiling point. 3C. That's it. Hopefully the video was helpful. I know it's a bit lengthy, but NMR is quite a difficult topic, so I need to try to get as much information in for you as possible. And that is it for organic chemistry. That is it. So past paper questions will be coming soon. Thank you very much for listening.